Hello students! This lecture will be on a method for finding derivatives known as implicit differentiation. For bivariate relations, the word bivariate means two variables. We'll go with x and y. Relations means that there's some relationship between them, usually given by an equation, that are not functions. We can still find instantaneous rates of change or tangent slopes. An example of a bivariate relation in the form of an equation is given right here. The set of all points that satisfy this equation can be plotted to produce some sort of graph. Now that graph is over here found using technology. Now this relationship between x and y is a non-functional relationship, meaning specifically that y is not a function of x, because here we have a vertical line that intersects the graph more than once, meaning there's more than one output for a single input. So y is not a function of x. But nor is x a function of y, because there are some choices of y that yield more than one x. The graph of this bivariate relation does not represent y as a function of x or x as a function of y. Despite that, you can still imagine a point, such as right there, and some sort of tangent line. Well, implicit differentiation will be the means for finding the slopes of these tangent lines, even when we're not working with functions. Now, given any xy equation, we're going to differentiate both sides with respect to x, meaning we treat x as the independent variable, while treating y as an unspecified yet implied function of x. This is called implicit differentiation, and we'll demonstrate it for this example. Specifically, our goal is to find all tangent lines to the bivariate curve below corresponding to x equals 0. In this graph, I can see 2 points when x is 0. One here appears to be at 0, 3, and a second point which appears to be at 0, -3. I'm imagining that the tangent lines I'm looking for are these two orange lines. One clearly has a positive slope and the other one a negative slope. So here's our equation. I need to differentiate both sides with respect to x. That means when I differentiate the right side of the equation, I would need to use the quotient rule, which if you would like to avoid, you can manipulate the equation prior to differentiation. So I'm actually going to multiply both sides of the equation by y prior to doing differentiation. So I'd get y squared plus y times x squared equals, and then just 9 plus 3x. If you can get the equation without any denominators, it will be easier to differentiate. And now we differentiate both sides with respect to x. A quick reminder, if you differentiate with respect to x cubed, you would get, using the power rule, just 3x squared, because x is the independent variable. But if you change that x base to any other letter, such as y, then we assume that this y is a function of the independent variable indicated by this x. So we would need to use the generalized power rule. So the 3 would drop down, the base would stay the same, power would drop to 2, but then we would multiply by the derivative of the base, y prime. With this in mind, when I differentiate y squared with respect to x, I'm going to get 2 times y to the first power, which I won't write because a 1 power looks like a prime, but then the chain rule times a y prime. Now for this derivative, we actually have a product. Y is an unknown function times x squared. Think of this as a UV product, and the derivative will be the derivative of the first. So the derivative of y, since we don't know what y is, we'll just say is y prime, times the second, plus the first, y, times the derivative of the second. And the derivative of x squared is just 2x, because x is the independent variable. And then we're done differentiating the left side. Now we say equal, and now we differentiate the right side. Well, the derivative of 9 is 0, and the derivative of 3x is just 3. There are no y's over here, so I do not expect to see any y primes on this side of my equal sign. Our next goal is to solve for y prime, which I see in 2 places. So every term that has a y prime, you gather or keep on one side of the equation. And any term, such as this one, that does not have a y prime, it has a y but not a y prime, you move to the other side of the equation. So we'll have 3 minus 2xy. Now we factor y prime, leaving 2y plus x squared, leave the other side the same, and then finally we divide to solve for y prime. And we get this expression. Now this y prime, another way to write it is to say dy dx. It's the rate of change in y with respect to x. It gives us the tools for finding the slope in the traditional sense, change in y over change in x. But notice our equation for the derivative also has y's in it, not just x's, like we're used to seeing up to this point. Well, that would make sense because saying that x needs to be 0 is not specific enough to know which point we're talking about, because there's a point here and a point here that both have x coordinates of 0. So it makes sense that you would need to know both x and y, plug them into this expression here in order to calculate the slope of a tangent line at any given point on this graph that's not a function. Well, first of all, let's confirm the y coordinates of the points before we proceed. So we want to find all points with x being 0. Well, you simply plug x equals 0 into the equation and then solve for y. So you have y plus 0 squared is equal to 9 plus 3 times 0, which is just 0, over a y. That gives me y equals 9 over y. If I multiply the y to the other side, I get y squared equals 9, and this confirms that y can be plus or minus 3. Confirming what we guessed, that one point is at 0, 3, and the other point in this graph is 0, negative 3. Okay, now we want to find the slope of the tangent line at the upper point. So we say, what is y prime when you plug in the point 0, 3? So this line is called an evaluation bar, and below it, you put down the data that you're plugging in. So now I look to this fraction, and I plug in 0 for all the x's and 3's for all the y's. So we get 3 minus 2 times 0 times 3, which will just be 0, over 2 times 3, which is 6, plus a 0. In the end, we get a 1/2. I'll call this M1, meaning the slope of our first point. The slope at our second point, we'll call that M2. We expect this one to be negative. So y prime at 0, negative 3 is equal to, we're going to have a 3 minus 0 again, and the denominator this time will be negative 6 plus 0. So we get negative 1/2 this time, and that's my M2. Let's call the upper one line 1 and the lower one line 2. So now let's find the equation of line 1. We can use point slope form. Y minus y1 is equal to m times x minus x1. We know the y coordinate of that point is 3. We know the slope is 1/2, and then x minus 0. So we get y minus 3 equals 1/2 of x, and then add 3, and put our answer in slope-intercept form. And here's my first line. Now for line 2, do y minus the y coordinate, so y minus negative 3 is y plus 3, is equal to, the slope of this line is negative 1/2 times x minus 0. That gives us y plus 3 is equal to negative 1/2 x, and then subtract 3. And here is the equation of line 2. Confirming with technology, I've typed in the equation after I multiplied both sides by y. You could also type in the equation before you multiply both sides by y. Let's type in the 2 points and then the 2 lines. I'll make them orange, dashed, and skinnier. And there we have the graph, which includes the 2 tangent lines that we were after. Okay, let's go to the next page. Find all tangent lines to the bivariate curve below corresponding to y equals 3. We have a graph here, which we made with technology. Y equals 3 is there, and I can see that there are 2 points that correspond to y being 3. Let's find out what those x coordinates are first. So we're going to let y be 3, and we'll solve for x, looking at this equation. So we have 3 is equal to x squared plus 2 times the sine of pi times 3 is the same thing as 3 pi. On the unit circle, we have pi, 2 pi, 3 pi, plus 1 full rotation and a half. The coordinates there are negative 1, 0 on the unit circle, and the second coordinate is the sine of 3 pi. So I know that sine of 3 pi is just 0. That means we're solving 3 equals x squared, so x will be plus or minus the square root of 3. So on the left, we have negative radical 3 comma 3 as my point, and on the right, we have positive radical 3 comma 3 as my point. We'll say line 1 is on the left, and line 2 is on the right. And now we have to find the slopes of these lines. So we'll use implicit differentiation. We'll differentiate both sides of the equation. I'll just put the entire equation in brackets and say we are going to find the derivative with respect to x. So the derivative of y with respect to x is simply y prime. Derivative of x squared will be 2x using the power rule. No chain rule required. Plus, now to differentiate 2 sine pi y, the 2 will stay. The derivative of sine is cosine. The argument stays the same, but then we multiply by the derivative of the argument. Well, the derivative of pi y, the pi will stay, and the derivative of y is just y prime. Now I notice that there are 2 different y primes, but they're on opposite sides of the equal sign, so I'm going to gather them on the same side by subtracting this entire term to the left side of the equation. So you have y prime, and then minus, I'll put this 2 and pi and y prime all in front of the trig function, 2 pi y prime, and then times cosine of pi y, equals, and the only thing left on the right side of the equation is 2x. Now I'll factor these y primes out of both terms, leaving 1 minus 2 pi cosine of pi y, and that equals 2x, and then finally we divide by everything in those parentheses. So y prime is equal to 2x all over 1 minus 2 pi cosine of pi y. And now we have the tools to find the slopes at each point. Let's go with this point first to find the slope of line 1. So y prime at the point negative rad 3, 3. We plug in x equals negative rad 3, so we have negative 2 rad 3 in the numerator over 1 minus 2 pi times the cosine, and we change y to 3 of 3 pi. Well, this first coordinate, which is negative 1 on our unit circle, is the cosine of 3 pi. So that'll be a negative 1. So we get a slope of negative 2 rad 3 over 1 plus 2 pi. And this is as much as we can simplify it. Now let's find y prime evaluated at positive rad 3, comma 3. That gives us positive 2 rad 3 over 1 minus 2 pi cosine of 3 pi. And this time we're going to get positive 2 rad 3 over 1 plus 2 pi. This first fraction we'll call the first slope and the second fraction the second slope. Okay, now to find the equations. For line 1, we do y minus the y coordinate, so y minus 3 is equal to the slope. This was negative 2 rad 3 over 1 plus 2 pi times x minus the x coordinate. So that's x minus negative rad 3 or x plus rad 3. I'm going to go ahead and distribute this slope. So that slope times x and then minus. And when I do rad 3 times this rad 3, I just get 3 times that negative 2 will be negative 6 over 1 plus 2 pi. And now add 3 to both sides. And we'll just leave our answer like this. And now for line 2. We have y minus 3 is equal to, and this slope was 2 rad 3 over 1 plus 2 pi times x minus rad 3. So a lot of similar simplification, and then add 3, and there's the equation of my second line. Notice that their slopes are opposite of each other. One is positive, one is negative. But the rest of the equation represents the y-intercept of this line, and that is the same for both lines, suggesting that these lines intersect each other on the y-axis, which by the symmetry of this graph appears to be the case. So in Desmos, I've typed in our equation to create our bivariate relationship. Here are the 2 points in question. Our first line gives us our tangent line for the first point. Then I'll duplicate this, change the slope to positive, and there's our tangent line at the second point. And sure enough, both lines have the same y-intercept. If you zoom in on a point, you can see better the tangent nature of this line to that curve. Okay, let's go on to the next problem. The bivariate curve below is an ellipse. Now remember, an ellipse is an oval. So here's some examples of ellipses. Ellipses have very special reflective properties, which we won't get into in this lecture. Find all points where the tangent line is horizontal and all points where the tangent line is vertical. Okay, let's begin by finding an expression for y prime by using implicit differentiation and differentiating both sides with respect to x. So the derivative of 2x squared will simply be 4x. The derivative of 4y will be 4 times y prime equals. The derivative of 8x is just 8. And the derivative of y squared is 2y to the first, and then chain rule times y prime. And then the derivative of 4 is 0. Right? There are 2 terms that have y primes. We want to get them on the same side. So I'm going to add this term to both sides. And there are 2 terms that don't have y prime. So I'm going to subtract this term from both sides. That gives me 4y prime plus 2y prime is equal to 8 minus 4x. Now I'll factor and then divide. I could simplify this a little bit further because I notice all the coefficients are even. So if I factor a 2 out of both the numerator and the denominator, then 2 over 2 is 1 and it can be canceled. So our final answer will be y prime is equal to 4 minus 2x over 2 plus y. Now in general, if you have a curve and a location where the tangent line is horizontal, that means the slope will be 0, which means the numerator of y prime needs to be 0. But if you have a point on the curve where the tangent line is vertical, here you would have the slope does not exist, which means that the numerator of y prime is not 0, but the denominator of y prime is 0, because non-zero over 0 indicates a infinite or vertical slope. So looking at my fraction that represents y prime, you set the numerator equal to 0 and solve, and we'll get x equals 2. This is where we'll have horizontal tangents. But you set the denominator equal to 0 and solve. This is where we will have vertical tangents. All right, so now let's focus on the horizontal tangents. We will let x be 2 and then solve for y. And we do this in the original equation, which is written here. Change all the x's to 2's and calculate. We get 2 squared is 4 times 2 is 8 plus 4y. 8 times 2 is 16 minus y squared plus 4. Let's gather all the terms on the left side of the equation. So I'll add the y squared over. We have plus of 4y. 16 plus 4 is 20, and subtract 20 from this 8. You have minus 12 is equal to 0. And we need to solve this for y. This is a quadratic equation. It will have 2 answers, which makes sense because in ellipse, you expect 2 points to have horizontal tangents. The question is, does this factor? In this case, it does. Y plus 6 and y minus 2. Confirm y times y is y squared, minus 2y plus 6y, that's plus 4y, and then minus 12. So that tells us y needs to be negative 6 or 2. So in conclusion, we have horizontal tangent lines at x was 2 and y was negative 6. and x was 2 and y was 2. Now for the vertical tangents, we're going to let y be negative 2 and solve for x. And again, we're looking at the original equation. So we have 2x squared plus 4 times y, and y is negative 2, so we have minus 8, is equal to 8 times x minus y squared. We'll square the negative 2, we get 4, so we say minus 4, and we have plus 4. The 4's will cancel, the 8x I'll subtract over, and I'll divide everything by 2, because I see everything is even, giving us this equation. This time, our equation does not factor, so we have to use the quadratic formula. Just as a reminder, if ax squared plus bx plus c is equal to 0, then the solutions to this equation can be found by doing x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. So in this case, we're going to get x equals a will be 1, b is minus 4, and so is c. So x equals negative b, which is 4, plus or minus the square root of b squared is negative 4 squared, which is 16, goes to positive, minus 4ac. And 4 times a times c will be negative 16. So we're subtracting negative 16, which means we're adding 16, all over 2 times a. This is radical 32. Square root of 32 can be simplified because 32 is 16 times 2. So we can write this as 4 square roots of 2, and then divide all the terms by 2. So in the end, we have 2 plus or minus 2 rad 2. So we have vertical tangent lines at one point will be x equals 2 minus 2 rad 2, comma, and the y coordinate is minus 2. And the other one is at 2 plus 2 rad 2, comma, negative 2. Okay, let's confirm this with technology. Here is the graph of our ellipse. We had horizontal tangents at 2, negative 6, and 2, 2, which is the top and the bottom of this ellipse. And we have vertical tangents at 2 minus 2 rad 2, comma, minus 2, and 2 plus 2 rad 2, comma, minus 2, which correspond to the major and minor vertices of this ellipse. Okay, let's go to the next page. During the loop of a roller coaster ride, a diamond ring fell from the pocket of a rider. The path of the roller coaster is modeled by the bivariate curve below called a strophoid. Here's our strophoid equation. It makes this loop, which models the loop of our roller coaster. Determine the trajectory of the ring, assuming it slipped away at the point in the first quadrant corresponding to y equals 2. So here's the line y equals 2, and the point we're after is this point right here. If you let go of the ring at this point in the roller coaster, it will have an initial trajectory that's in the direction of the tangent line. And then, of course, it would follow a parabolic arch as it falls to the ground. But its initial trajectory, as it's released from the roller coaster, would be along this line. So finding the slope of this line would be crucial to getting our initial trajectory of the ring. So let's find the x-coordinate there first. So we're going to change y equals 2, and we'll solve for x, into the original equation. So we have 3x squared plus x squared times y is 2, so 2x squared, equals 5y squared, y is 2, so we have 4 times 5 is 20, minus 2 cubed, which is 8. So that gives us 5x squared is equal to 12, x squared is equal to 12 fifths. So x will be plus or minus the square root of 12 fifths. Now we only want the first quadrant point here, so we'll go with positive square root of 12 fifths is the x-coordinate and the y-coordinate is 2. Now let's take our strophoid equation and differentiate both sides of it. So I'll just put the entire equation in brackets with respect to x. So the derivative of 3x squared is 6x. Here we need to use the product rule, because if x squared times y, that's a product of two functions. So we do the derivative of the first, which is the derivative of x squared, which is 2x, times the second, plus the first times the derivative of the second, and the derivative of y is y prime, equals. Now we need to use the generalized power rule both here and here, because y is an unknown function. So the derivative of 5y squared would be 10y to the first, but then times y prime, chain rule, and then minus 3y squared times y prime, chain rule. Now all the terms that have y prime, I'm going to gather but on the right side of the equation, and these two terms that don't have y prime, I'll just leave where they are. So you have 6x plus 2xy is equal to, I'll write these two terms first, 10y, y prime, minus 3y squared, y prime, and then we have this term here that I need to subtract over there, minus x squared, y prime. Now I can factor the y prime out of all three of those, leaving me 10y minus 3y squared minus x squared, all times y prime, and then we can find y prime now by dividing. So we have 6x plus 2xy in the numerator divided by 10y minus 3y squared minus x squared. So we want y prime specifically at the point radical 12 fifths comma 2. So we change all the x's to this radical and all the y's to 2. This y will turn into a 2 times the 2 coefficient will become 4 radical 12 fifths. Change both these y's to 2's. We'll have 20 minus 12, which is 8, minus, and then square x gives me just 12 fifths. We could take this a little bit further. The two terms in the numerator are similar. So we have 10 radical 12/5. This 8 needs a denominator of 5, so we'll change it to 40/5 minus 12/5 is 28/5. Now we'll invert and multiply. I'll simplify just a little bit further. 10 and 28 have common factors. That's 5 over 14. And then times that 5, so we'll have 25 over 14 times the square root of 12/5. This is a good point where I'm just going to round it. And we get a slope of about 2.766. This would be the first bit of useful information in trying to determine the trajectory of the ring, as it would then follow a parabolic arch back towards the ground. And then we could predict where it might land. Keep in mind the meaning of this slope. To have a slope of 2.766 means that at a starting point, if you go right 1 unit, you would need to go up 2.766 units, revealing the initial trajectory of the ring. Okay, this concludes our lecture on implicit differentiation to find tangent lines to curves that aren't necessarily functions of x or functions of y.